There is an object predicted by the laws of physics that nothing in the universe can enter. Not a wall, not a barrier you could theoretically breach with enough energy. A boundary written into the structure of space-time itself, where the rules run in one direction only, outward. Matter streams away from it. Light pours out of it. And nothing, not a single particle, not a single photon, can ever cross inward through its surface. This object is called a white hole. It is not science fiction. It is not a speculative metaphor. It is a direct solution to Einstein's equations of general relativity, sitting in the mathematics with exactly as much legitimacy as the black holes we have already photographed. Think about what that contrast means. A black hole pulls everything in. Its event horizon is a one-way surface that matter and light can cross inward but never cross back out. Once you're inside, you're not coming out. A white hole is the precise opposite. Its horizon is a one-way surface that matter and light can cross outward but never cross back in. Once something is inside, it will inevitably exit, and nothing from outside can ever get in. One object is a cosmic drain. The other is a cosmic fountain. The same equations that give us the drain give us the fountain, with equal mathematical force. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Most people have heard of black holes. Most people have at least some sense of what they do. But white holes are almost never discussed, and the reason isn't that they're less interesting. It's that they're more unsettling. A black hole fits our intuitions about how extreme physics works. Gravity gets strong enough, things get trapped, nothing escapes. We can picture that. A white hole demands something harder. It demands an object that permanently ejects material from an interior that can never be accessed from outside. It demands a region of space-time with a past but no way in. That combination doesn't fit anything in our everyday experience, and it doesn't fit most of what we know about how the universe operates. So the obvious question is this: what is actually inside it? If nothing can enter a white hole from the outside, what lives behind that boundary? Is there matter in there? Is there structure? Is there a singularity like the one at the heart of a black hole, or something entirely different? The answer, it turns out, requires us to pull apart our assumptions about time itself. Inside a white hole, the geometry of space-time runs backward relative to a black hole interior. Where a black hole has a singularity in its future, a point that everything inside must eventually reach, a white hole has a singularity in its past. Everything inside is moving away from it. The interior isn't collapsing. It's expanding. It behaves less like a compressed point and more like a tiny universe flying apart from an origin. That description should feel familiar. It should feel familiar because it sounds like the early universe. It sounds like the Big Bang, and that is not a coincidence. It is one of the deepest threads running through white hole physics, and we'll get to it. But before we can talk about what's inside, we have to build up the full picture carefully. We have to understand the thermodynamics, the instability arguments, the quantum gravity proposals that have recently brought white holes back from theoretical irrelevance, and the question of whether physics as we know it allows these objects to exist at all, not just in equations, but in reality. Because here's what most people don't realize. The mathematics permits white holes unconditionally. The same laws of physics that describe every black hole ever detected also describe their mirror image. The universe's equations hand us both objects and decline to choose between them. Whether the universe itself makes that choice, and what it would mean if it doesn't, is one of the genuinely open questions in modern physics. It touches the information paradox, the origin of the cosmos, and the nature of time at its most fundamental level. To understand what's inside a white hole, we first have to understand what a white hole actually is, and that starts with the mathematics that accidentally created one. In 1915, Carl Schwarzschild was doing artillery calculations on the Eastern Front when he solved Einstein's field equations and inadvertently discovered something that would puzzle physicists for over a century. Think about what that means. Einstein had published his general theory of relativity just weeks earlier. The ink was barely dry, and here was a soldier in a war zone, working through the mathematics in between artillery computations, finding an exact solution to equations that Einstein himself hadn't fully solved yet. Schwarzschild sent his work to Einstein in a letter from the front. Einstein was astonished. He presented the solution to the Prussian Academy of Sciences in January of 1916. Schwarzschild died at the front a few months later, never knowing what his equations would eventually reveal. What Schwarzschild had found was a description of spacetime around a perfectly spherical, non-rotating, uncharged mass, a star essentially, reduced to its simplest possible form. The solution described how space and time curve in the presence of that mass. It told you the path that light and matter would follow near it. It was clean. It was exact. It was one of the most important results in the history of physics. But the solution contained something strange. At a certain critical distance from the center, a distance we now call the Schwarzschild radius, the equations produced a boundary where something extreme happened. Gravity became so intense that not even light could escape. Cross that boundary inward, and you couldn't get back out. This was a black hole. Nobody called it that in 1916. That term wouldn't exist for another half-century. But the mathematics described one perfectly. For decades, most physicists thought the Schwarzschild radius was a mathematical curiosity, a pathological feature of the equations. Surely, they reasoned, nothing real could produce such an extreme object. Einstein himself doubted that black holes could physically exist. The mathematics was correct, but physics, they assumed, would intervene before anything collapsed that far. They were wrong about that, but that isn't the surprise we're focused on here. The real surprise was hiding inside the time structure of the equations themselves. General relativity is built on a framework where space and time are woven together into a single four-dimensional fabric called spacetime. The equations that govern this fabric, Einstein's field equations, have a property that isn't immediately obvious. They are time-symmetric. There's no preferred direction of time built into them. Forward and backward are treated identically by the mathematics. This seems abstract, but it has a concrete consequence. If you take the Schwarzschild solution describing a black hole and reverse the direction of time in the equations, you get a new solution, a valid one that satisfies Einstein's field equations just as perfectly as the original. And this new solution describes something different, where the black hole was an object that matter and light could only fall into, never escape. This time-reversed solution described an object that matter and light could only escape from, never enter, a white hole. The equations didn't flag this as unusual. They didn't produce an error. They simply handed back a second answer, equally well-formed, equally consistent with the rules of general relativity, pointing in the opposite direction. For a while, this was noticed, but not formalized. It sat in the background of theoretical work on general relativity through the 1950s and early 1960s, acknowledged but not developed. Then in 1964, a Soviet physicist named Igor Novikov brought the white hole into focus as a distinct theoretical object worth taking seriously. Novikov recognized that the extended mathematical description of the Schwarzschild spacetime didn't just contain a black hole and its exterior. It contained four separate regions. The exterior we're familiar with, the black hole interior, where everything falls toward a future singularity, a second exterior region, a mirror copy, and the white hole interior, where everything emerges from a past singularity. Novikov proposed that white holes might actually be observable. He even suggested they could explain quasars, which were newly discovered at the time, and producing enormous amounts of energy from compact regions in distant galaxies. That specific idea didn't survive contact with better data, but the formalization stuck. Here's what makes this genuinely surprising. The two solutions aren't related the way a correct answer and a wrong answer are related. They're not related the way a useful approximation and an exact result are related. They're two complete, exact, internally consistent descriptions of possible objects, derived from the same starting equations with the same status in the mathematics. The equations of general relativity give you a black hole, and they give you a white hole, and they treat both with equal indifference. Consider what that requires you to accept. The most successful theory of gravity we have, the framework that predicted gravitational waves before we could detect them, that described the bending of light around the sun with extraordinary precision, that underlies the GPS systems you use every day, that theory, when you ask it what objects can exist in the universe, hands you back two answers. One absorbs everything, one emits everything. Neither answer is preferred, neither is marked as the real one. The equations don't know about entropy. They don't have a built-in arrow of time. They don't care that we live in a universe where things tend to fall apart rather than assemble themselves. They only know geometry. And in the geometry of general relativity, a black hole and a white hole are mirror images with identical mathematical standing. Some physicists looked at this and concluded that the white hole solution was a formal artifact. The equations are time-symmetric, they argued, but the universe isn't. Our universe has an arrow of time. Cause precedes effect. Entropy increases. The black hole solution aligns with that arrow and the white hole solution runs against it. So the universe selects one and discards the other. The mathematics is more permissive than reality, maybe. But that argument assumes we understand why the universe has an arrow of time in the first place, which is itself one of the deepest unsolved problems in physics. Both solutions sit there in the mathematics, equally valid, equally real by the standards of the equations. And that means the question isn't whether white holes are mathematically possible, but whether the universe is obligated to care about math. A white hole has an event horizon, just like a black hole, but the horizon works in precisely the opposite direction. To understand what that means, start with what a black hole's horizon actually does. When you fall toward a black hole, its event horizon lies in your future. You can reach it, you can cross it. In fact, once you're close enough, you cannot avoid crossing it. The geometry of space-time makes the horizon your inescapable destination. The horizon is a one-way membrane, and the direction it permits is inward. Light can fall in, matter can fall in, information can fall in. Nothing comes back out. A white hole's horizon is the exact reverse. It lies in your past, not your future. You cannot reach it, cannot approach it, cannot cross it from the outside. The horizon is still a one-way membrane, but the direction it permits is outward. Things come out, nothing goes in. If you were floating in space near a white hole, you could watch material streaming away from its boundary, light pouring out, particles emerging from what looks like empty space at the edge of a defined region. And you could not touch that boundary. You could not send a radio signal across it. You could not throw a rock through it. You could fire a laser directly at the horizon, and that beam of light would never make it across. Think about what that actually looks like from a distance. You are an observer, let's say a few light years away from a white hole. What do you see? You see a region of space with a defined boundary, a horizon, just like a black hole's. But instead of light bending inward and disappearing, you see light bending outward. Material is streaming away from the horizon in all directions. Radiation is flowing away from it. Particles are appearing at the boundary and moving outward into space. There is no obvious source. Nothing is exploding. Nothing is burning. Matter and energy simply emerge continuously from the boundary of this region and spread outward into the surrounding universe. A black hole is a drain. Everything nearby gets pulled toward the center, crosses the horizon, disappears. A white hole is a fountain. Everything inside continuously moves outward, crosses the horizon from the inside, and escapes. These two objects are geometric opposites, and yet the same equations describe both of them. Here is a concrete way to hold on to the difference. Imagine a river with a waterfall. Water flows toward the edge and drops over. You can float in the river, get carried toward the falls, and go over. That's a black hole, a current you can enter and follow to its end. Now reverse the entire process. Water flows upward, gathers at the top of the falls, and flows outward in every direction across a flat surface. You are standing on that surface. No matter which direction you move, you are moving away from the center, carried by the current. And you cannot move back. You cannot swim against it. That reversed waterfall is a white hole. You are already on the outside of it, being pushed away, and you cannot reach the source no matter how hard you try. The distinction between a past horizon and a future horizon is worth sitting with because it's where most of the strangeness lives. When physicists talk about a black hole's event horizon, they mean a surface in spacetime that lies in the causal future of an outside observer. You can reach that surface. It takes time. If you fall toward a black hole, your world line, your path through spacetime, will eventually intersect the horizon. The horizon is ahead of you. A white hole's horizon is a surface that lies in your causal past. It's behind you, in the sense that your path through spacetime moves away from it. You can never return to it. You can never approach it. From the moment you exist as an observer near a white hole, you are already moving away from its horizon, because that horizon is a boundary in your past, not something waiting for you in your future. It's the same reason you can't travel back in time to yesterday, not because there's a wall blocking you, but because the structure of space-time simply doesn't permit that direction of travel. This is genuinely strange to think about. A black hole horizon is something you can fall into accidentally. If you drifted too close without realizing it, you would cross the horizon without any particular sensation, tidal forces permitting, and not realize what had happened until you tried to send a signal back and found it impossible. A white hole horizon cannot be stumbled into. It cannot be entered at all. You would have to have always been on the outside of it, receding from it, unable to close the gap no matter what you did. What does the material coming out of a white hole look like? General relativity doesn't fully specify what kind of matter or radiation emerges. That depends on initial conditions set deep inside the white hole's interior. But the outflow is real and continuous. Light escapes, particles escape. Energy pours across the horizon and spreads into the surrounding space. If a white hole had the mass of a star, its gravitational field outside the horizon would look identical to a star's gravitational field. You would orbit it the same way. Gravity pulls toward it, just as it pulls toward any massive object. But the horizon itself remains completely sealed from the outside. You could orbit a white hole for billions of years and never get inside. There is something almost paradoxical about this. The gravity of a white hole pulls things toward it, the same as any massive object, but the horizon actively prevents anything from actually arriving. Matter falling toward the white hole from outside would approach the horizon, get closer and closer, and never cross. The outflowing material from inside the white hole would be streaming outward through that same region of space, creating a boundary where infalling material from outside and outflowing material from inside meet at the horizon without either being able to pass through. The result is a kind of standoff at the edge of the white hole, which turns out to be related to one of the reasons white holes are so difficult to sustain. But that comes later. The basic picture is this. A black hole is defined by what it takes in. A white hole is defined by what it gives out. They have the same geometry, the same mass, the same gravitational field at a distance, and the same kind of event horizon. But that horizon points in opposite directions through time, and that single difference makes them about as different as two objects in physics can possibly be. One represents the ultimate in absorption, the other represents the ultimate in emission, and the second law of thermodynamics, which governs every physical process we have ever observed, has strong opinions about which one of these can actually exist in a universe like ours. All of that is strange enough on its own, but the truly disorienting question isn't what a white hole does from the outside. It's what exists on the inside, behind that boundary that nothing can ever cross inward. To see what lies inside a white hole, you have to look at the complete mathematical picture of what the Schwarzschild solution actually describes. And when you do, 4 separate regions of space-time appear. Most people, when they think about a black hole, picture 2 things: the outside, where everything is normal, and the inside, where everything falls toward a singularity. That's not wrong, but it's incomplete. The Schwarzschild solution, when you extend it fully, without cutting any corners, without throwing away the parts that seem uncomfortable, describes something far stranger. It describes a universe with 4 distinct regions of space-time, all of them connected, all of them real by the standards of the mathematics. Physicists call this the Kruskal-Szekeres extension. It's named for the 2 mathematicians who independently worked out the complete picture in 1960. And what they found was not just a black hole. It was a black hole, a white hole, the universe we live in, and a second separate universe, all woven together into a single geometric structure. Think of the Kruskal diagram as a map of all of space-time around a Schwarzschild mass. On this map, time runs vertically, space runs horizontally. Light always travels at exactly 45-degree angles. Nothing can travel faster than light, so nothing on this map can move at an angle steeper than 45 degrees from vertical. That constraint, that simple rule about light, is what defines which regions of space-time can talk to each other and which cannot. 2 diagonal lines cross at the center of the diagram. Those lines are the event horizons. They divide the entire map into 4 quadrants. The right quadrant is where we live, the exterior. Normal space-time, a region where you can move freely, observe the mass from a distance, and choose to stay away from it. The upper quadrant is the black hole interior. The lower quadrant is the white hole interior. And the left quadrant is a second exterior region, a mirror of ours, causally disconnected, unreachable, a separate universe sharing the same geometry. The upper quadrant, the black hole interior, has a specific and terrifying property. The singularity sits at the top. On the Kruskal diagram, it appears as a horizontal line across the ceiling of that region. And because nothing can travel faster than light, because every possible path you can take through space-time is constrained to move within those 45-degree light cones, every single path inside the black hole points upward, toward that line. You cannot avoid it. You cannot turn around. The singularity isn't a place in space that you can steer away from. It's a moment in time that lies in your future. All futures inside a black hole lead to the same place. That's what it means when physicists say the singularity is inevitable. Now look at the lower quadrant, the white hole interior. The singularity there appears as a horizontal line at the bottom, the floor of that region, not the ceiling. It's a past singularity. It lies behind everything inside the white hole, not ahead of it. And because the light cone constraint still applies, because every path through space-time still has to move within those 45-degree angles, every possible path inside the white hole points upward and outward, away from the singularity, toward the exterior. The geometry of the white hole interior is the exact time reverse of the black hole interior. Where the black hole interior forces convergence on a future singularity, the white hole interior forces divergence from a past one. That distinction matters more than it might initially sound. In a black hole, space-time is structured like a funnel. Everything moves inward and downward toward a single inevitable point. The curvature of space-time itself creates a current that nothing can swim against. In a white hole, space-time is structured like the opposite of a funnel. Everything moves outward and upward, away from the origin. The current runs the other direction. And just as you cannot escape a black hole once you've crossed its horizon, you cannot remain inside a white hole. The geometry will not permit it. Every path leads out. There is no staying. There is no hovering. There is no orbit around the interior. The white hole pushes everything toward its horizon and past it and out into the exterior region. It isn't a prison. It's an ejection mechanism written into the shape of space-time. This is worth sitting with for a moment. Inside a black hole, the singularity is your future. Inside a white hole, the singularity is your past. One is a destination, the other is an origin. The entire character of the interior changes based on that single distinction about where the singularity sits in time. The matter inside a white hole isn't collapsing, it's expanding. Space-time itself is stretching outward from the origin point, carrying whatever exists inside it toward the exterior. This is why physicists sometimes describe the white hole interior as resembling a rapidly expanding universe, more than a compressed object. The geometry has the structure of a cosmological expansion, not a gravitational collapse. Matter and energy don't accumulate at a center. They spread, they separate, they move apart from each other as the interior geometry drives them all toward the single allowed exit, the event horizon through which they will eventually emerge. Now here is where the Kruskal diagram becomes genuinely disorienting. Look at the two horizons crossing at the center. The diagonal line running from lower left to upper right is the black hole horizon. Once you cross it inward, you're in the upper quadrant, inside the black hole, heading toward the future singularity. The diagonal line running from lower right to upper left is the white hole horizon. Nothing from the exterior can cross that horizon inward. Nothing. Any signal, any particle, any observer approaching from outside, they simply cannot get in. The horizon recedes before them at the speed of light. But matter already inside the white hole, in that lower quadrant, can cross that horizon outward. Outward crossing is allowed. Inward crossing is not. The white hole horizon is a one-way valve, but it runs the opposite direction from the black hole horizon. This asymmetry reveals something profound about the deep structure of spacetime. The black hole and white hole horizons are not merely different objects located in different quadrants. They are expressions of the same geometric surface, viewed from opposite temporal directions. A signal that cannot penetrate the white hole horizon from outside is locked out by the same space-time curvature that permits nothing to escape the black hole horizon from within. The difference lies not in the physics, but in the direction of time. From the perspective of an observer in the exterior region, the white hole horizon appears as an impenetrable barrier protecting whatever lies beyond it. But from the perspective of someone hypothetically inside the white hole interior, that same barrier appears as a one-way gate, pulling everything toward the outside. The two views describe the same surface through opposite arrows of causality, a perfect mirror image in time. Most people, when they learn this, ask the same question. If nothing can get into the white hole interior from outside, where did whatever is inside it come from? The answer the mathematics gives is straightforward and strange. It came from the past singularity. The white hole interior is sourced from the bottom of the Kruskal diagram. That past singularity is the origin of everything inside it. Whatever matter or energy exists in the white hole interior emerged from that singularity and has been expanding outward ever since. You did not fall into the white hole. You were born from it. The second exterior region, the left quadrant on the Kruskal diagram, adds another layer to this. It exists. It's real within the mathematics, a separate region of space-time, structurally identical to ours, on the other side of the geometric structure. Observers in that universe and observers in our universe both see the same mass, both experience the same gravitational effects from a distance, and yet cannot communicate with each other. No signal can pass from one exterior to the other. The white hole interior is below both of them, connected to both. the source of matter that could in principle emerge into either one. The black hole interior is above both of them, receiving matter that falls in from either side. The whole structure is symmetric in a way that feels almost too clean to be describing physical reality. The boundary conditions in these two regions are fundamentally different from what we're used to. In the black hole interior, conditions are set at the start, initial conditions that determine how things fall toward the singularity. In the white hole interior, the conditions are set at the end, final conditions. The geometry specifies where things are going, not where they came from. This reversal of causality is part of what makes the white hole interior so conceptually difficult. We're accustomed to thinking about physics as a process that evolves forward from initial conditions. The white hole interior runs the other direction. It's a region where outcomes are fixed and histories are free to vary. What the Kruskal-Szekeres extension shows very clearly is that the Schwarzschild solution was always describing all four of these regions simultaneously. The common description of a black hole, an object you can fall into, is correct, but it's only one quadrant of the full picture. The full picture includes a white hole by necessity. You cannot have the Schwarzschild geometry without the white hole interior. It's not an addition or a modification. It's already there, in the same solution, in the same mathematics, in the same set of equations that describes everything we know about black holes. The white hole isn't a separate hypothesis. It's the other half of the same object. And what fills that interior? A space-time that expands outward from a past singularity. A geometry that drives everything inside it toward escape. A region where every path, every trajectory, every possible future for any object already inside it points toward the same exit. The arrow of time inside a white hole runs toward the outside. Not toward a crushing end, but toward a boundary that will eventually be crossed, that must eventually be crossed, that the structure of space-time itself demands be crossed. There is no way to stay. There is no inward direction. There is only the outward geometry, the expanding interior, and the horizon waiting ahead. The interior of a white hole isn't a place you can fall into. It's a place you can only fall out of, expanding away from a past singularity that no longer exists, moving toward an exit that cannot be refused. The mathematics works perfectly, and the geometry is internally consistent. But there is a law in physics so fundamental that it governs everything from the cooling of coffee to the death of stars, and white holes appear to violate it completely. That law is the second law of thermodynamics. It states that the total entropy of a closed system always increases over time. Entropy is a measure of disorder, of how many ways the components of a system can be arranged. A gas expanding into a vacuum increases entropy. A hot object cooling down increases entropy. A building crumbling into rubble increases entropy. The reverse of any of these processes would decrease entropy, and the reverse never happens on its own. Never. Not once in the history of human observation has a gas spontaneously compressed itself back into a corner, or a crumbled building reassembled into a standing structure without something else doing the work. Think about a raw egg dropped on a kitchen floor. It shatters. The shell fragments scatter. The yolk and white spread across the surface. That event increases entropy dramatically. The ordered, structured egg becomes a disordered mess. Now imagine the reverse, the yolk and white pulling themselves back together, the shell fragments flying upward, rejoining along every crack line, sealing perfectly, the egg lifting from the floor, fully intact. You have never seen that. No one has. The laws of physics don't technically forbid it at the level of individual particles. Every microscopic interaction is reversible in principle. But the probability of all those particles spontaneously moving in exactly the right directions at exactly the right times is so vanishingly small that it effectively never occurs. Effectively, but not precisely, never. That distinction matters. A white hole does something very similar to a reassembling egg. It takes whatever material is inside it and ejects it outward through the horizon. That material emerges into the universe as structured, outward-moving matter and radiation. The interior, that expanding region away from the past singularity, is producing output. And crucially, nothing is falling in to supply energy to that process. Nothing can fall in. The horizon prevents it. The white hole is generating output without any input, organizing and ejecting matter in a way that runs contrary to the direction every other physical process in the universe moves. Consider a simpler version of this. Take a glass of water with a drop of ink in it. You watch the ink diffuse. It spreads through the water, evenly distributing, until the entire glass has a faint uniform color. That's entropy increasing. The ink goes from ordered, concentrated in one spot, to disordered, spread throughout. You have never watched a uniformly colored glass of water spontaneously concentrate all its ink back into a single drop. Not because the physics forbids each individual molecular collision, but because the net probability of all those collisions happening to push the ink back together is essentially zero. The second law isn't a statement about what particles can do. It's a statement about what they almost certainly won't do, expressed so consistently across every scale of the physical world that physicists treat it as absolute. Black holes are completely consistent with this law. Matter falls inward. It gets compressed, shredded, mixed. Information that was once structured, the specific arrangement of atoms in a star, the internal chemistry of a planet, gets scrambled beyond any practical recovery. Entropy goes up. The universe moves in the expected direction. A black hole is essentially a maximum entropy object for its mass. You cannot get more disordered than a black hole of a given size. It is the universe doing exactly what the second law demands. A white hole runs every part of that process backward. The material coming out of a white hole is not increasing in disorder as it moves. It is moving from the highly curved, dense region near the past singularity outward toward the relatively flat spacetime outside the horizon. If anything, it is moving from more extreme conditions to less extreme ones. The universe outside a white hole would receive material without having done anything to cause it. No gravitational collapse drove matter in. No energy input organized the outgoing stream. The white hole interior simply expands and exits, and that exit looks, thermodynamically, like a catastrophic violation of everything the second law guarantees. Now here is where the problem compounds, because it isn't just that a white hole's operation would decrease entropy, it's that creating a white hole in the first place would require an even more staggering decrease in entropy. Black holes form through a process we understand completely. A massive star exhausts its nuclear fuel. The core collapses under gravity. The outer layers either fall inward or explode outward. The result is a black hole. Every stage of that process increases entropy. The ordered structure of the star gives way to the maximum entropy state of the black hole. Formation and operation are both thermodynamically natural. What would the time-reversed version of that look like? Start with a black hole. Watch it begin to shrink. Watch material flow outward from the horizon in an organized stream. Watch that stream gradually assemble itself into a stellar structure. Shells of gas pulling together. Nuclear processes running in reverse. A star reconstituting itself from outflowing plasma and radiation. Every step of that process decreases entropy. The spread out, disordered remnants of stellar death would have to spontaneously organize back into a star. That is not a small improbability. It is not a slightly unlikely event waiting for the right conditions. It is an entropy decrease so massive that there is no physical mechanism in the known universe capable of producing it. The second law is why time has a direction. It is why cause precedes effect. It is why you remember your past and not your future. The asymmetry between the past and the future that every human being experiences directly. The sense that things change and cannot be unchanged. That asymmetry is entropy. It is the second law playing out at every scale simultaneously. From the quantum interactions in your neurons to the expansion of galaxy clusters across billions of light years, a white hole would require that arrow of time to reverse, at least locally, without explanation. Most people who encounter white holes as a concept focus on the geometric strangeness, the horizon that works backward, the singularity in the past, the expanding interior. That is strange enough, but the thermodynamic problem is the deeper one. The geometry can be written down in equations, and it holds together. The thermodynamics points to something the equations cannot fully address. The universe has a history, and that history has a direction, and white holes point the wrong way down it. Not slightly wrong, completely, fundamentally, categorically wrong. There is no adjustment you can make to a white hole to bring it into alignment with the second law while keeping it a white hole. The violation is the mechanism. And so for a long time, that was roughly the conclusion most physicists reached. The math is valid, the geometry is consistent, but the universe we actually live in is governed by an entropy law that appears to make white holes not just rare, not just difficult, but impossible to form through any process we know of or could plausibly conceive. The second law doesn't just make white holes unlikely, it makes their formation in a universe like ours almost philosophically impossible, which is why physicists spent decades treating them as a mathematical curiosity with no physical reality, until someone started looking more carefully at what happens when a black hole gets very, very old. Even setting the thermodynamics problem aside, there is a second and more immediate reason why white holes cannot survive in a classical universe. They destroy themselves. The thermodynamics argument is about formation, about why a universe governed by increasing entropy would never produce a white hole in the first place. But the instability argument is different. It says that even if you somehow had a white hole, already existing, already operating, already pouring matter and radiation outward through its horizon, it would not survive, not for long, not even close to long. The timescales involved aren't millions of years or thousands. We're talking about essentially immediate collapse by cosmic standards. A white hole is not just difficult to create. It cannot hold itself together once it exists. In 1974, a physicist named Douglas Eardley worked through the mathematics of what happens to a white hole when the surrounding space-time isn't perfectly smooth. Think about what that means in practice. The real universe is not smooth. There is always something nearby. Gas clouds, radiation fields, the faint gravitational ripples produced by matter distributed unevenly across billions of light years. The universe is full of tiny perturbations. They're everywhere. And Eardley showed that any one of them, even an arbitrarily small disturbance in the space-time geometry from the distant past, would be enough to destabilize a white hole completely. The white hole wouldn't wobble and recover. It wouldn't ring down like a bell and settle into a new stable configuration. It would collapse. It would flip. It would become a black hole almost instantly. That word, instantly, needs some weight behind it. We're not talking about a slow degradation. A small perturbation traveling inward toward the white hole horizon would interact with the outflowing material trying to leave. Those two streams of matter and energy would meet at the horizon. And when they met, the energy densities at that boundary would climb toward catastrophic levels. The horizon region would become a site of extreme, destabilizing energy accumulation. Before anything inside the white hole had a real chance to escape, the structure would have already converted itself into the very thing it was supposed to be the opposite of. Compare that to a black hole. Black holes are remarkably stable objects. If you disturb a black hole, send a burst of gravitational waves through it, drop a mass into it, perturb it in any of dozens of ways, it responds in a predictable manner. It oscillates. Physicists call these quasi-normal modes. The black hole rings like a struck bell at specific frequencies determined by its mass and spin. Then it settles. The perturbation damps away. the black hole returns to a stable state. This is not a minor technical detail. It means black holes are attractors. The universe keeps producing them, keeps arriving at them, keeps settling into them as a natural endpoint of gravitational collapse. They're robust. They persist. White holes are the opposite of attractors. They're repellers. Every perturbation pushes the system away from the white hole configuration rather than back toward it. The pencil balanced on its tip analogy is exactly right here. The pencil satisfies the laws of physics in that position. You can write down the equations. The solution exists. It's valid. But place that pencil in a real room with real air and real vibrations in the floor, and it falls. Immediately. Every time. The solution is mathematically genuine and physically useless. And Erdely's result was only the beginning. The same year, Zeldovich, Novikov, and Starobinsky approached the problem from a different angle entirely. They weren't looking at classical perturbations from outside the white hole. They were looking at what quantum field theory does near the white hole's horizon from the inside. When they calculated the quantum corrections to what physicists call the stress-energy tensor, essentially a mathematical description of the energy and momentum content of the space near the horizon, the numbers didn't just get large, they diverged. They blew up. The quantum corrections to the energy density at the white hole horizon went to infinity. What that means physically is this: the vacuum of space near a white hole's horizon is not quiet. Quantum field theory tells us the vacuum is never truly empty. It seethes with fluctuations, virtual particles, zero-point energy. Near a black hole horizon, these quantum effects produce Hawking radiation, a slow and steady emission of real particles as the black hole loses mass. That process is gradual, it's manageable. The black hole persists for an enormous amount of time before quantum effects become important. But near a white hole horizon, the quantum corrections don't stay small. They diverge right at the horizon. The structure of the white hole undermines itself from the inside out, at the quantum level, independently of anything falling in from outside. So you have two separate mechanisms, discovered in the same year by different researchers using different methods, both arriving at the same conclusion. Classically, Erdely shows a white hole collapses from external perturbations. Quantum mechanically, Zeldovich, Novikov, and Starobinsky show it destabilizes from internal quantum corrections. Neither result depends on the other. They reinforce each other. Together, they made a strong case that white holes, even granted the extraordinary assumption that one somehow formed, were not survivable structures. Think about what this means for the matter inside a white hole. In the mathematical picture of white hole geometry, the interior contains material that originated at a past singularity and is moving outward toward the horizon. In principle, that material should exit. It should cross the horizon and emerge into the exterior universe. But in practice, the exterior universe is filled with infalling matter and radiation. And that infalling material hits the outflowing material at the horizon before the exit can happen. The collision point becomes a zone of extreme energy density. The white hole collapses before its interior contents reach the outside. Whatever was inside never gets out. The picture by the mid-1970s was fairly complete, and it was bleak for white holes. The thermodynamics argument said the universe wouldn't make them. The classical instability argument said they couldn't survive external perturbations. The quantum instability argument said they couldn't survive external perturbations. The quantum instability argument said they undermined themselves from within. Three separate lines of evidence. Three separate failures. White holes remained a legitimate piece of the extended Schwarzschild geometry. You could still write them down, still point to them in the Kruskal diagram, still describe their mathematical properties, but as physical objects capable of existing and operating in the real universe, they seemed to be ruled out at every level of analysis. For most of the late 20th century, that was roughly where white holes stood. Beautiful mathematics, lethal physics, No realistic path to existence. And then loop quantum gravity offered something nobody expected, a way for a black hole to become one. Loop quantum gravity starts from a simple but radical premise. Space-time is not a smooth, continuous fabric, but a network of discrete quantum units. And at small enough scales, the geometry of space itself becomes grainy. Think about what that means. We tend to picture space as a kind of backdrop, infinite, featureless, something that objects move through rather than something that has structure of its own. General relativity changed that. It told us space curves. It bends around mass. It stretches and compresses. But general relativity still treats space-time as fundamentally smooth, continuous, like a perfectly flat sheet of rubber that can be warped but never torn. Loop quantum gravity challenges that assumption at the deepest level. It says space isn't a smooth sheet at all. It's woven from discrete quantum units called spin networks. At the Planck scale, around 10 to the negative 35 meters, space has a texture, a granularity. Below that scale, the concept of smooth, continuous geometry simply stops applying. There is no smaller distance. There is no finer resolution. Space itself has a minimum size. That sounds abstract, but the consequences are concrete. And the most important consequence has to do with what happens inside a black hole. In classical general relativity, the story inside a black hole ends badly. Everything that falls in eventually reaches the singularity. Not eventually in the sense of a long time from now. Eventually in the sense that every possible path, every possible direction you could travel, every geodesic through the interior space-time, all of them point toward it. The singularity isn't a place at the center of the black hole in space. It's a moment in the future, a moment that nothing can avoid. At the singularity, density becomes infinite. Curvature becomes infinite. The equations of general relativity produce results that are meaningless. Physics breaks down completely. Most physicists treat the singularity as a sign that general relativity is incomplete. That something is missing from the theory, something that would take over at extreme densities and prevent the infinite collapse from actually occurring. Loop quantum gravity proposes that the missing ingredient is quantum geometry. When matter collapses inward and space-time curvature approaches the Planck scale, quantum effects become dominant. The discrete structure of space-time itself generates a kind of pressure, not a physical pressure in the ordinary sense, a geometric resistance. The minimum grain size of space means that curvature cannot increase without bound. Density cannot reach infinity. There is a ceiling, a maximum density set by the quantum nature of space-time, somewhere around the Planck density, which is approximately 5 times 10 to the 96 kilograms per cubic meter. That number is incomprehensible. It's so far beyond anything we can produce or measure that it essentially exists only in equations. But it's finite. And that finite ceiling changes everything. When collapsing matter hits that ceiling, it doesn't continue collapsing. It bounces. The quantum pressure reverses the contraction. The interior of the black hole, instead of converging toward a point of infinite density, reaches a maximum compression and then begins to expand outward again. This is what loop quantum gravity researchers call the quantum bounce. It replaces the singularity with a transition, a moment of maximum density with everything moving outward toward an exit, is exactly what a white hole interior looks like. This is the key insight. The bounce doesn't destroy the black hole, it transforms it. Carlo Rovelli and Hal Haggard published work formalizing this picture in 2014. Their framework described a black hole that forms, collapses to a Planck density core, undergoes a quantum bounce, and then begins expanding outward as a white hole. The event horizon of the original black hole doesn't disappear, it transitions. The inward-pointing horizon of the black hole becomes the outward-pointing horizon of the white hole. Matter that spent millions or billions of years falling inward begins to re-emerge, not destroyed, not lost. preserved through the bounce and now expanding back out into the universe. The black hole doesn't evaporate in the Hawking sense here. It doesn't slowly radiate away into nothing over astronomical timescales. It transitions on a different mechanism entirely. The interior geometry flips. The singularity that once lay in the future of every infalling particle is replaced by a past singularity, the kind that defines a white hole interior. Everything that fell in begins to move toward the horizon, not pulled, pushed by the geometry of expanding spacetime. Now here is where things get genuinely strange. The timescales involved are almost impossible to reconcile. From inside the black hole, from the perspective of the infalling matter, the quantum bounce happens quickly. The matter collapses. It reaches the Planck density. It bounces. The whole interior transition in the reference frame of the collapsing material takes a short time. Not instantaneous, but brief on cosmological scales. The physics inside the bounce region is exotic and extreme, but it doesn't drag on for billions of years. From outside the black hole, the picture is radically different. The event horizon is a region of extreme time dilation. Clocks slow down near the horizon. An observer hovering just outside the horizon of a stellar mass black hole would see infalling objects appearing to freeze at the horizon surface, never actually crossing. The closer you get to the horizon, the more dramatically time dilates. What takes a fraction of a second in the interior can correspond to an enormous span of time as seen from outside. For a stellar mass black hole, a black hole with a mass roughly equal to a few of our suns, the transition time as seen from the outside could exceed the current age of the universe by a lot. We're talking timescales so vast that the universe as we know it would be unrecognizable before any signal of the transition reached a distant observer. The black hole sits there, from our perspective, completely stable, absorbing, growing, nothing escaping, and yet inside, across the horizon we can never observe directly. The bounce has already happened, or is in the process of happening. The quantum geometry is already in its expansion phase. The interior is already, in some sense, a white hole. We just can't see it yet. This is genuinely difficult to hold in your mind. The inside and the outside of a black hole don't share the same present. There's no universal clock that ticks the same way for an observer at infinity and an observer near the horizon. The transition that is brief for infalling matter is cosmologically slow for anyone watching from a safe distance. Both are real. Both are correct descriptions of the same event. They just don't correspond to the same slice of time. The mass of the black hole determines how long this takes. The more massive the black hole, the longer the transition takes from the outside. Small black holes, if any primordial ones formed in the early universe and have survived, might be completing their transitions on timescales we could actually observe. Rovelli and others have speculated that some of the most energetic and mysterious transient events we detect, fast radio bursts among them, might be signatures of these transitions. Primordial black holes small enough and old enough to be finishing their quantum bounce right now, briefly blazing as white holes for a fraction of a second before going quiet. The numbers are uncertain. The connection to fast radio bursts is speculative, but the prediction is testable in principle, which H is more than can be said for many proposals in quantum gravity. What this picture does, fundamentally, is connect the two objects we've been discussing throughout this video. The black hole and the white hole aren't separate exotic objects that happen to be mathematical mirrors of each other. They're two phases of the same object. The black hole phase involves the horizon pointing inward, matter collapsing, curvature rising. The white hole phase involves the horizon pointing outward, matter emerging, curvature decreasing. And the quantum bounce is the mechanism that connects them. It's the hinge, the moment where one phase becomes the other. This doesn't resolve all the problems. The thermodynamic objections we covered earlier don't simply vanish because of loop quantum gravity. The entropy question remains genuinely difficult. The details of the bounce, the precise dynamics of the transition, the exact quantum state of the emerging matter, these are active areas of research with significant uncertainty. Different researchers within the LQG community reach different conclusions about the details. The broad picture has substantial support. The fine-grained mechanics are still being worked out. But what loop quantum gravity provides that nothing before it did is a specific, mathematically grounded mechanism by which a white hole can actually come to exist. Not by forming from scratch through some process that would require violating thermodynamics, not by emerging from nothing, but by being the natural continuation of a black hole that has completed its interior evolution. Every black hole that forms carries within it the seed of a white hole. The bounce is built into the geometry of quantum spacetime. It's not a special condition that has to be arranged. It's what happens when general relativity meets quantum physics at the Planck scale. In this picture, every black hole that has ever formed is slowly, almost imperceptibly, becoming a white hole, and the ones that are small enough and old enough might already be in the process of transition right now. When Stephen Hawking calculated in 1974 that black holes slowly evaporate, he inadvertently created one of the deepest problems in theoretical physics. The problem starts with quantum mechanics. Quantum mechanics is not just a theory about small things. It's a precise mathematical framework that describes the behavior of every particle, every field, every interaction at the fundamental level. And one of its most basic requirements is that information cannot be destroyed, not hidden, not scrambled, not destroyed. The quantum state of a system at any moment, in principle, contains the complete history of that system. You can run the equations forward, you can run them backward. The information is always there. This is called unitarity, and it's not a minor technical point. It's one of the core pillars the entire structure rests on. Now think about what happens when something falls into a black hole. A star collapses. A cloud of gas spirals inward. An astronaut crosses the event horizon. Whatever crosses that boundary carries information with it. The precise quantum state of every particle involved. The specific arrangement of atoms, the spin states of electrons, the exact configuration of fields, all of it goes in. And according to classical general relativity, none of it comes out. The event horizon is a one-way surface. That information is trapped behind it, locked inside, seemingly forever. For a long time, physicists were willing to live with that. Information might be inaccessible, hidden deep inside an object that nothing can escape. But hidden isn't the same as destroyed. The information was still there, encoded in whatever was inside the black hole. That was uncomfortable, but it wasn't a catastrophe. Then Hawking changed everything. What Hawking showed is that black holes aren't completely black. The vacuum of space near a black hole's event horizon behaves in a specific and strange way. Quantum field theory tells us that empty space is not truly empty. It seethes with virtual particle pairs, particles and antiparticles flickering into existence and annihilating each other in fractions of a second, borrowing energy from the vacuum and returning it almost instantly. Near the event horizon, something different happens. A pair of virtual particles can form right at the boundary. One particle falls inward across the horizon. The other escapes outward into space. The escaping particle carries real energy away from the black hole. The black hole loses mass to compensate. Over time, vast amounts of time, this process chips away at the black hole. A stellar mass black hole would take something on the order of 10 to the 67th years to evaporate completely through Hawking radiation. That number dwarfs the current age of the universe by an almost incomprehensible margin. But eventually, in principle, the black hole is gone. That's when the problem becomes catastrophic. The Hawking radiation that carries the black hole's mass away appears to be thermal. It's random. It carries no record of what fell in. A black hole formed from a collapsed star produces essentially the same Hawking radiation as a black hole formed from an equal mass of anything else. The radiation depends on the mass, the charge, and the spin of the black hole, and nothing else. All the detailed information about what fell in, every quantum state, every configuration of every particle has apparently been erased. By the time the black hole finishes evaporating, that information is gone. Not hidden. Gone. This is a direct contradiction between two theories that have both been spectacularly confirmed by experiment. General relativity describes how spacetime curves around mass. Quantum mechanics describes how particles and fields behave at the smallest scales. Both theories work. Both theories pass every experimental test we throw at them. And yet, applied together to the situation of an evaporating black hole, they produce an impossibility. One says information can be destroyed. The other says it cannot. They cannot both be right. This is the information paradox. Physicists have been arguing about it for 50 years. Some proposed that information escapes gradually, encoded in subtle correlations in the Hawking radiation over the black hole's lifetime, that the radiation only looks thermal but actually carries quantum information in a form too complex to detect directly. This is the most widely accepted approach today, associated with the idea of black hole complementarity and later the firewall debate. Others proposed that information gets stored in a Planck-scale remnant after evaporation, a tiny, stable object holding everything the black hole ever swallowed. Others suggested new physics at the horizon, modifications to quantum mechanics, or that the paradox reveals a fundamental incompleteness in our understanding of space-time itself. Most of these solutions require something significant to break. Either quantum mechanics gets modified, or general relativity gets modified, or some entirely new principle gets introduced that nobody has yet identified. None of them are clean. All of them carry costs. The white hole scenario is different. It doesn't require breaking anything. Recall what loop quantum gravity suggests about the fate of a black hole. The singularity at the center is not a point of infinite density where physics collapses. It's a region of extreme but finite curvature where quantum effects become dominant and the geometry bounces. Instead of compressing matter toward a mathematical point that destroys all structure, the interior reaches a maximum density determined by the Planck scale and then rebounds. That rebound is the birth of the white hole interior. The collapsing black hole transitions from the inside out into an expanding white hole. What does this mean for the information? Everything that fell into the black hole over its entire lifetime is still there. It's encoded in the quantum state of the matter compressed inside the bounce region. That matter doesn't vanish at a singularity. It survives the bounce. It becomes part of the expanding white hole interior, carried outward from the past singularity toward the horizon. And as the white hole ejects material through its horizon, that material carries the information with it, all of it. The complete quantum record of everything the black hole ever swallowed eventually emerges. Think about what that means. A star falls in. A planet falls in. An astronaut falls in. Over millions or billions of years, all of it accumulates in the black hole interior. In the classical picture, it all converges on a singularity and the information is destroyed. In the white hole picture, the singularity is replaced by a bounce. Everything survives. Everything eventually comes back out, transformed but not erased. The quantum state of the universe is preserved. Unitarity is satisfied. Quantum mechanics is not broken. General relativity is not broken. No exotic new principle is required. The only modification is to the deep interior of the black hole, at scales where quantum gravity effects already have to apply regardless. You don't need to change anything about how black holes look from the outside. You don't need to change the rules of quantum mechanics. You don't need to introduce firewalls or remnants or modifications to the event horizon. The information paradox dissolves because the singularity dissolves. This is genuinely unusual in theoretical physics. Most proposed resolutions to the information paradox are complicated. They involve new degrees of freedom at the horizon, subtle non-local effects stretching across vast distances, or modifications to quantum mechanics that would have observable consequences in other experiments. The white hole transition doesn't need any of that. It works with the physics we already have, extended into the regime where quantum gravity becomes relevant. That's a regime we knew was going to require new physics anyway. The white hole scenario just uses that new physics to solve two problems at once: the singularity and the information paradox, with a single mechanism. There's something worth pausing on here. The information paradox is one of the reasons theoretical physicists have spent decades building frameworks like string theory and loop quantum gravity. It's a genuine contradiction sitting at the foundation of our best theories. The fact that a specific, concrete proposal, the black hole to white hole transition, resolves it without requiring anything dramatic above the horizon is the kind of simplicity that physicists find compelling. Not because simplicity guarantees truth, but because the history of physics suggests that when two major problems share one clean solution, that solution is worth pursuing seriously. Whether or not the white hole scenario is correct, the fact that it resolves the information paradox so cleanly without breaking either quantum mechanics or general relativity is exactly the kind of thing physicists take seriously, even when they're skeptical. There is a version of cosmology in which the Big Bang was not a beginning at all, but an exit. That's not a poetic reframing. It's a direct consequence of the mathematics we covered in the last section. We showed that a white hole has a past singularity at its core, a point from which everything inside expands outward, carried by the geometry of space-time itself, unable to reverse course, destined to cross the horizon and emerge. Now consider what the Big Bang looks like when you describe it precisely. A singularity in the past. Matter and energy expanding outward in every direction. No path that leads backward through it. Nothing that came before it, at least not in any way the standard model can describe. That's not a loose analogy to a white hole interior. That is a white hole interior. The geometry is, in the words of physicists who have actually worked through the equations, mathematically identical. Think about what that means for a moment. The most important event in the history of the universe, the one that produced every galaxy, every star, every atom, may have been an object we haven't yet detected, an exit point, a past horizon that our entire observable universe has been pouring out of for 13.8 billion years. We've been asking what lies inside a white hole. One answer the mathematics keeps returning to is this: everything we can see. Let's back up and build this carefully. In standard Big Bang cosmology, the universe begins at a singularity, a moment of infinite density and temperature, roughly 13.8 billion years ago. Before that singularity, the standard equations give us nothing. Not empty space, not time passing slowly, just nothing that the mathematics can describe. General relativity breaks down at that point. The singularity is a wall. The model begins there and moves forward, and asking what came before is technically undefined within the framework. Most cosmologists have treated that boundary as a genuine beginning. The universe simply started. But here's what most people don't realize. General relativity producing a singularity is a sign that general relativity is incomplete, not that the singularity is physically real. We've already seen this in the black hole context. Loop quantum gravity replaces the black hole's future singularity with a quantum bounce. Density reaches the Planck scale, roughly 10 to the negative 93 grams per cubic centimeter, and quantum pressure halts the collapse. The same logic applies to the Big Bang singularity. If space-time is granular at the Planck scale, the singularity at the beginning of the universe doesn't have to be a true singularity. It could be a bounce point, a moment of maximum density, finite and physically real, from which the universe rebounded outward. This is the big bounce. Instead of the universe emerging from nothing, it emerged from a maximum density state that was itself the final stage of a previous collapsing universe. A prior universe contracted under gravity, reached Planck scale density, and bounced. The energy and matter of that collapse didn't compress into an infinitely small point and disappear. They compressed to the limit that quantum geometry allows and then exploded outward into the expansion we call the Big Bang. Our universe isn't the first act, it's the second, and the phase from which it erupted, the expanding outward from a past singularity, pouring matter and radiation through a boundary that nothing can cross inward. That's the white hole phase. Our Big Bang was the white hole exit of a previous collapse. Haggard and Rovelli, working within the framework of loop quantum gravity, made this connection explicit. They showed that the geometry describing a black hole interior that has undergone a quantum bounce and begun expanding outward is the same geometry that describes the early universe, not approximately the same. Mathematically identical, at times precisely so. The space-time structure is the same. The causal structure is the same. The relationship between the singularity and the horizon is the same. You can take the equations describing the interior of an expanding white hole, and they describe the Big Bang cosmology without modification. This matters enormously. It means the Big Bang wasn't a special one-off event that required the universe to appear from nothing. It was an instance of something the laws of physics already describe: a white hole. The equations already had this solution. We just hadn't recognized what we were looking at. Now consider the cosmic microwave background. This is the oldest light we can detect. Radiation from roughly 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and photons to travel freely. Before that moment, the universe was opaque. We can't see past it with ordinary light. That's our observational horizon. In the Big Bounce picture, that radiation, the oldest light in the universe, represents the earliest observable emission from the white hole event that produced our cosmos. It's the afterglow of the exit. Some theorists look at the cosmic microwave background for anomalies, specific patterns in the temperature fluctuations that might carry imprints of the pre-bounce phase, information about the collapsing universe that came before. If the Big Bounce happened, it may have left faint signatures in that ancient light. The search is ongoing. The signals, if they exist, are subtle, but the target is clear. Now take the final step. If the Big Bang was the white hole phase of a previous collapse, and if the universe we inhabit is the interior of that white hole, expanding outward from a past singularity, unable to reverse, destined to cross the horizon eventually, then we are not outside a white hole looking in. We are inside one, right now. Every cubic meter of space around you is part of the expanding interior of a white hole that has been erupting outward for nearly 14 billion years. The galaxies aren't flying apart because of some mysterious force pushing them. They're flying apart because they're inside a white hole interior. And that's what the geometry of a white hole interior does. It expands. It diverges. It spreads everything outward from a point in the past. That's not as strange as it sounds once you hold the geometry clearly. A white hole interior is a region where everything moves away from a past singularity toward a future horizon. An expanding universe is a region where everything moves away from a past singularity, the Big Bang, toward a future we can't yet see beyond. Strip away the labels and the descriptions are the same. This reframes the question we started with in a profound way. We've been asking what lies inside a white hole as if it's something out there, some exotic object we might find at the edge of the universe, something a future telescope might image the way we've imaged black hole shadows. But if this picture is correct, the interior of a white hole isn't somewhere else, it's here. The answer to the question isn't a location in space, it's the space itself. Not everyone accepts this picture. It depends on loop quantum gravity being the correct approach to quantum gravity, and that hasn't been confirmed. It depends on the Big Bang singularity being resolved by a quantum bounce rather than by some other mechanism. There are cosmologists who find the Big Bounce compelling and cosmologists who find it speculative. That's honest. The evidence isn't in yet. But the mathematical correspondence between the Big Bang geometry and the white hole interior isn't a matter of debate. It's there in the equations, and it's exact. If that picture is correct, then the question of what lies inside a white hole has a startling answer. Everything. Every galaxy, every star, every atom of every person who has ever lived, all of it expanding outward from a past singularity that fired off the universe we inhabit. When you write down the complete mathematical description of the Schwarzschild black hole without making any simplifying assumptions, something unexpected appears, a second universe. Not a metaphor, not a poetic way of describing something strange, a second, fully separate region of space-time, with its own exterior, its own stars and planets in principle, its own version of everything that exists on our side, entirely disconnected from ours, yet joined to ours through the interior geometry of a single black hole. Most people who hear about the Schwarzschild solution hear about the black hole. They hear about the event horizon and the singularity at the center. But the complete solution contains 4 distinct regions of spacetime, not 2. And when you map all 4 of them out, what you find event, and sitting between the 2 exterior regions is something Einstein and Nathan-Rosen identified in 1935, a bridge, what we now call a wormhole. To see how this works, you need what physicists call the Kruskal-Szekeres extension of the Schwarzschild solution. The original Schwarzschild coordinates break down at the event horizon. The math produces what looks like an error, a division by 0. For decades, physicists debated whether this was a real physical problem or just a problem with the coordinates. It turned out to be the coordinates. When you switch to Kruskal-Szekeres coordinates, the breakdown disappears. The full geometry of space-time becomes visible, and what becomes visible is 4 quadrants. The exterior region on the right, our universe, the space outside the black hole interior above, the region where everything that crosses the horizon falls toward the future singularity, a second exterior region, O. In the left, a mirror universe, causally disconnected from ours, and below, the white hole interior, the region expanding away from a past singularity, the region everything inside is inevitably ejected from. 2 universes, 2 singularities, 1 black hole, 1 white hole, all packed into the geometry of a single, non-rotating, uncharged mass. Think about what that means. The simplest possible black hole, no spin, no charge, just mass, contains within its mathematics a complete second universe, not hidden, not optional. It's just there, sitting in the equations, unavoidable once you extend the solution properly. The 2 exterior regions occupy the same position in the Kruskal diagram, in a sense. They're both outside the horizons. They both look like normal space-time from a distance, but they are causally separated. Nothing that originates in our exterior region can reach the other. No light signal, no particle, no information. You cannot send a message from one side to the other. They share the singularity, they share the interior geometry, but they cannot communicate. The connection between them runs through the white hole interior below and the black hole interior above, specifically through the wormhole, the Einstein-Rosen bridge. In the Kruskal diagram, the 2 exterior regions are joined at a single point. That point is the throat of the bridge. At one instant in time, there exists a geometric connection between the 2 universes, a narrow passage through the interior. This is what Einstein and Rosen found in 1935 when they were studying the Schwarzschild solution. They found the bridge. They thought it might be a model for particles, that electrons and protons might be tiny wormholes in space-time. That idea didn't work out. But the bridge itself was real mathematics. It's still there in the solution. Here's the problem. The bridge doesn't stay open. It forms and collapses. It forms and collapses so fast that nothing can cross it. Light traveling at 186,000 miles per second, cannot make it through before the throat pinches off. There is no moment in time where both exterior regions are connected long enough for a signal to pass. The wormhole exists. It is traversable in 0 seconds. That's not traversable. To actually cross from one universe to the other through the Einstein-Rosen bridge, you would need to travel faster than light. General relativity forbids this. The bridge is real and unreachable at the same time. It's a connection that connects nothing in practice. This is where Roger Penrose's proposal comes in. Penrose and others have suggested that matter falling into a black hole in our universe might emerge through a white hole in another universe entirely. Not through the Einstein-Rosen bridge in the classical sense, but through the full Kruskal structure, with the black hole interior on one side and the white hole interior delivering material into the second exterior region. On paper, this is geometrically consistent. Material falls across the black hole horizon from our universe. Inside the black hole, it moves toward the future singularity. But if quantum effects replace the singularity, as loop quantum gravity suggests, the material could bounce and begin moving outward through the white hole interior instead. It would then emerge through the white hole horizon into the second exterior, into the other universe. It's a remarkable idea. Black holes as cosmic drains on one side, white holes as cosmic fountains on the other. Matter flowing from one universe to another through the interior geometry. It sounds almost elegant. The problem is the white hole horizon. We covered the instabilities earlier. The fact that any infalling material from outside the white hole interacts catastrophically with the outflowing material at the horizon. Any matter that fell into the black hole from our universe, when it finally reaches the white hole horizon and attempts to emerge into the second exterior region, would encounter those instabilities. The energy densities at the boundary would be extreme. The geometry would be destabilized. Whatever was trying to emerge probably wouldn't make it out intact. The connection is one way. It's irreversible. And it's almost certainly lethal to anything passing through. What survives this picture is the geometry itself. Even if nothing physical can cross, even if the bridge collapses instantly and the white hole horizon destroys everything near it, the structure is still there in the mathematics. Two universes joined at a point, sharing an interior that contains both a black hole and a white hole, with a wormhole throat between them that forms and vanishes before light can blink. No other object in theoretical physics packs this much geometry into such a simple description. A single mass, no rotation, no charge, just mass. And from that, Einstein's equations produce two universes, a black hole, a white hole, and a tunnel between them that can never be used. Most stars end their lives without producing anything like this. They collapse, they fade, they leave behind neutron stars or stellar mass black holes, quiet remnants of what they once were. But the mathematics describing even the most ordinary black hole carries all of this hidden inside it. The second universe is in there. The white hole interior is in there. The wormhole is in there. It has always been in there, since Schwarzschild first wrote down the solution on the Eastern Front in 1915. We just didn't know how to read it yet. The Einstein-Rosen bridge exists in the mathematics, but the universe that sits on the other side of it is permanently, irrevocably out of reach, at least through any known physical process. If white holes exist, whether as the endpoints of dying black holes, as primordial relics from the Big Bang, or as transitions driven by quantum gravity, they would leave signatures that astronomers could potentially detect. The question is what those signatures would look like, and whether we already have instruments sensitive enough to find them. That's not a trivial problem. The universe is an extraordinarily noisy place. Energetic events happen constantly, across every wavelength of light. And separating a white hole signal from everything else requires knowing precisely what you're looking for before you start. Let's start with the most direct prediction. In the loop quantum gravity picture, a black hole doesn't evaporate quietly into nothing. It transitions. It bounces. The matter that collapsed inward reaches a maximum density set by quantum effects, reverses, and begins expanding outward as a white hole interior. From outside, this looks like an explosion, a sudden burst of radiation streaming away from a point in space where, for millions or billions of years, there was only a black hole. The energy released would be enormous. The burst would be brief, and it would arrive from essentially any direction in the sky, because primordial black holes, if they formed in the early universe, in the first fractions of a second after the Big Bang, would be scattered throughout space with no particular preference for galaxies or clusters. They'd just be there, invisible, aging, and eventually going off. Carlo Rovelli and others have pointed specifically at fast radio bursts as a candidate signal. Fast radio bursts are exactly what they sound like: brief, intense, radio pulses lasting milliseconds, arriving from cosmological distances, carrying enormous amounts of energy. The first one was discovered in archival data in 2007. Since then, hundreds have been catalogued. Some repeat, most don't. No single explanation accounts for all of them cleanly. Neutron-star mergers have been proposed. Magnetar flares are currently the leading explanation for at least some bursts, but the population is diverse, and there's genuine uncertainty about whether one mechanism explains everything we're seeing or whether there are multiple sources contributing to the sample. The primordial black hole transition scenario fits some of what we observe. A white hole explosion from a small primordial black hole completing its quantum bounce would produce a burst of radiation. The duration and energy of that burst would depend on the mass of the original black hole. Smaller black holes complete their transition faster. Their bursts would be shorter and harder to resolve. Larger ones would produce longer, potentially brighter events. If the black hole started with a mass on the order of what could have formed in the early universe and has been aging for roughly the current age of the universe, the timing works. These objects would be finishing their transitions right now, or relatively close to now on cosmological timescales. Think about what that means. There could be primordial black holes completing their quantum bounce at this moment, releasing radiation we could detect, if we knew exactly what wavelength to look at and how to distinguish the signal from background. But here's what most people don't realize about this search. The theoretical prediction isn't precise enough yet to make a definitive identification. Loop quantum gravity gives us the broad picture. Black hole bounces to white hole, emits radiation, but the detailed spectrum of that radiation, its precise duration, its angular distribution, depends on aspects of quantum gravity we haven't fully worked out. We're looking for something without a completely finished description of what it looks like. That's a real limitation. It doesn't make the search pointless. It makes the search preliminary. Astronomers are accumulating data while theorists refine the predictions, and eventually, those two tracks need to converge on something specific enough to test. Gamma-ray bursts are another candidate worth considering. They're more energetic than fast radio bursts, some lasting only fractions of a second, others stretching for minutes. The short-duration ones, under 2 seconds, are generally associated with neutron star mergers. The long-duration ones with the collapse of massive stars. But within both populations, there are outliers. Events that don't fit the standard template. Some short bursts have been detected with no obvious host galaxy, no identified merger site, no clear progenitor. That doesn't mean they're white holes. It means we don't know what they are, and that uncertainty is exactly the kind of gap where a new explanation might eventually fit. The cosmic microwave background offers a completely different line of investigation. The CMB is the oldest light in the universe. Radiation released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. It's been mapped with extraordinary precision. Its temperature fluctuations, tiny variations of 1 part in 100,000, encode information about the state of the early universe. If the Big Bang was not a true beginning but a bounce, a white hole transition from a previous phase of the universe, that pre-bounce history might have left imprints in the CMB, specific patterns, anomalies that don't fit the standard inflationary picture cleanly. Several researchers have looked for these signatures. There are features in the CMB data that have generated debate: a cold spot, anomalies in the power spectrum at large angular scales, but none have been firmly identified as evidence of a pre-Big Bang phase. They could be statistical flukes. They could be instrumental artifacts. They could be something else entirely. The data is there. The interpretation is contested. What makes this search genuinely difficult is that white holes, if they exist, would look a lot like other things. A brief burst of high-energy radiation from an unknown point source could be a magnetar. A gamma-ray burst with no identified host could be a distant neutron-star merger caught at an unfavorable angle. An anomaly in the CMB could be a foreground contamination effect. The universe doesn't label its phenomena. It just produces signals, and we have to figure out what generated them. Ruling out every alternative explanation before concluding that something is a white hole would require extraordinary evidence. That's not a counsel of despair. That's just how science works at the frontier. The next generation of instruments is genuinely more capable than what we had a decade ago. The square-kilometer array will detect fast radio bursts with far greater sensitivity and localization precision than current telescopes. New gamma-ray observatories will expand the sample of well-characterized bursts. Future CMB experiments will map the polarization of the microwave background with higher fidelity, potentially revealing patterns invisible to current surveys. If the theoretical predictions sharpen at the same time the observational capabilities improve, the window for an actual detection gets meaningfully wider. That's not a guarantee. It's a realistic assessment of what the next decade might offer. No one has yet found an unambiguous white hole signal in any of these observations, but the search is ongoing, and the instruments looking for it are getting better every year. Hawking radiation changed the way physicists think about black holes. When you apply the same reasoning to white holes, the result is strange in a different way. In 1974, Stephen Hawking showed that black holes aren't perfectly black. Quantum field theory near the event horizon changes everything. Empty space isn't truly empty. The vacuum constantly produces pairs of virtual particles, a particle and its antiparticle, that flicker into existence and almost immediately annihilate each other. Near a black hole's event horizon, something different happens. One particle from the pair falls across the horizon into the black hole. The other escapes. From a distance, that escaping particle looks like radiation streaming away from the black hole. The black hole has emitted something. It loses a tiny amount of mass in the process. Over an almost incomprehensible span of time, this slow leak continues. The black hole shrinks. Eventually, in principle, it evaporates entirely. Think about what that means for a stellar mass black hole. The Hawking temperature of such an object is roughly 60 billionths of a degree above absolute zero. That's not a temperature we can measure with any instrument we currently possess. The radiation is so faint, so cold that it's completely buried beneath the cosmic microwave background, which sits at about 2.7 Kelvin. We can't observe Hawking radiation directly from any known black hole, but the mathematics is solid. The physics community accepts it, and it has consequences that reach much further than anyone expected. Now apply the same logic to a white hole. Time reversal symmetry is strict here. If a black hole produces radiation by separating virtual pairs at its horizon, with one particle falling in and one escaping out, then a white hole should do the exact reverse. Instead of emitting thermal radiation outward, a white hole would absorb thermal radiation from its surroundings. Pairs still form near the horizon, but now the particle that escapes falls inward toward the white hole. The one that would have fallen in gets ejected outward. The energy flows in the opposite direction. The white hole gains mass rather than losing it. The temperature of this inverse process turns out to be mathematically identical in form to the Hawking temperature. The same equation, the same dependence on mass, the same relationship to the surface gravity of the horizon. The only difference is the direction of the energy flux. One object radiates outward, the other absorbs inward. Both processes are governed by the same underlying quantum mechanics. But here's where it gets genuinely strange. Hawking himself recognized something unsettling about the picture. A black hole in thermal equilibrium with its surrounding radiation, absorbing exactly as much as it emits, would have to be time-symmetric in its boundary conditions. It can't have a preferred direction of time if it's in perfect balance. And when you write down the boundary conditions for a black hole in perfect thermal equilibrium, they become mathematically indistinguishable from the boundary conditions for a white hole. The two objects, which seem like complete opposites in every physical sense, converge on the same description at the quantum level when you push the analysis far enough. Most black holes in the universe aren't in thermal equilibrium with their surroundings. The cosmic microwave background is warmer than the Hawking temperature of any stellar mass or supermassive black hole. So they're actually absorbing more radiation than they emit right now. They're gaining mass, not losing it. The equilibrium case is theoretical, but the theoretical case reveals something real about the underlying structure of the physics. That black holes and white holes aren't as cleanly separated by quantum mechanics as they appear to be by classical geometry. Now consider isolated white holes. If primordial white holes exist, relics from the early universe or the endpoints of ancient black hole transitions, they should be radiating, not through the inverse absorption process, but through a quantum process of their own. Theoretical work suggests that isolated white holes produce quasi-thermal radiation that resembles Hawking radiation in its statistical properties. The spectrum wouldn't be identical, but it would carry the same thermal character. If you detected it without knowing its source, you might not immediately recognize it as coming from a white hole rather than a black hole. This circles back to the observational search. Any primordial white hole small enough to be in the final stages of its existence would be radiating intensely. A very small white hole, one with the mass of a mountain compressed into a region smaller than a proton, would be producing radiation at temperatures billions of degrees above absolute zero. The final moments of such an object would be an energetic burst. Some researchers have pointed to fast radio bursts and gamma-ray bursts as potential candidates for this kind of signal. The connection isn't confirmed, but it isn't ruled out either. There's a deeper implication underneath all of this. The fact that the quantum description of a black hole in equilibrium blurs into the quantum description of a white hole suggests that the classical distinction, one absorbs, one emits, they are opposites, might be an oversimplification. Classical general relativity gives us two clean, separate solutions. Quantum mechanics, when applied carefully to the horizons of both objects, starts to smear that boundary. The two objects might be different aspects of the same quantum system, viewed from different boundary conditions, different initial states, different arrangements of the vacuum. We don't have a complete quantum theory of gravity. That gap is exactly where the uncertainty lives. But the pattern is suggestive. Every time physicists have looked carefully at the quantum behavior of horizons, the distinction between black holes and white holes has gotten less sharp, not more. At the quantum level, the clean distinction between a black hole and a white hole, one that absorbs, one that emits, begins to blur into something more complicated and, if anything, more interesting. General relativity doesn't care about the direction of time. Write down the equations that describe a black hole, run time backward through them, and you get a perfectly valid solution. The mathematics doesn't resist. It doesn't flag an error. It just gives you a white hole, as cleanly and indifferently as it gave you the black hole in the first place. Both solutions satisfy the same equations. Both are mathematically legitimate. And yet the universe is full of black holes and contains, as far as we can tell, 0 white holes. That asymmetry is not written into the equations. It comes from somewhere else entirely. Think about what that means. The laws of physics, at their deepest level, treat the past and the future as interchangeable. Drop a ball and film it. Run the film forward, the ball falls. Run the film backward, the ball rises. Both versions are consistent with Newtonian mechanics. The same logic applies to electromagnetism, to quantum mechanics, to general relativity. The fundamental equations of physics work equally well in either direction, and yet no one has ever watched a shattered glass reassemble itself off the floor. No one has ever seen smoke funnel back down into a chimney. The future is not interchangeable with the past. Something is breaking the symmetry, and it isn't the equations. That something is entropy. Entropy is a measure of disorder in a system, and it increases. Always. In every isolated system we have ever studied, entropy moves in one direction. This is the second law of thermodynamics, and it is the reason the past looks different from the future. It is the reason causes come before effects. It is the reason you remember yesterday, but not tomorrow. The arrow of time, the sense that time has a direction at all, is entropy doing its work. And the question of why white holes don't exist turns out to be the same question as why entropy increases in the first place. The answer goes back to the Big Bang. When the universe began, roughly 13.8 billion years ago, it started in an extraordinarily low entropy state. Think about how strange that is. The universe was hot, dense, and compressed into an almost incomprehensibly small volume. By some intuitions, that sounds like maximum disorder. But entropy isn't just about how compressed things are, it's about how many possible arrangements a system could be in. And the early universe, for all its heat and density, was remarkably smooth, remarkably uniform, remarkably ordered in its gravitational configuration. Gravity had not yet had the chance to clump matter into stars, galaxies, and black holes. That clumping is what increases gravitational entropy. The early universe was gravitationally simple. That simplicity represented a profound state of order. Everything since the Big Bang has been the universe relaxing away from that initial improbable condition. Stars form because gravity pulls matter together, entropy increasing. Stars burn through their fuel and collapse, entropy increasing. Black holes swallow material and scramble the information it carried, entropy increasing. The entire history of the cosmos, from the first hydrogen atoms to the last evaporating black holes, is a story of entropy climbing toward higher and higher values. Black holes fit naturally into this story. They are, in a sense, the endpoint of the process. When you fall into a black hole, your information is scrambled. Disorder grows. The universe moves in the direction it has always been moving. White holes run the film backward. A white hole takes whatever is inside it and ejects it outward. In the loop quantum gravity picture, the material that spent billions of years falling into a black hole eventually emerges through the white hole transition. That emergence is the reverse of the process that created the black hole in the first place. It is entropy decreasing, locally, dramatically, in a way that cuts against the entire current of cosmic history. The second law of thermodynamics doesn't just make this unlikely. In a universe with the initial conditions ours has, it makes it an almost unimaginable exception. Here is the deeper point, and this is where it gets genuinely disorienting. The time reversal symmetry of general relativity isn't violated by white holes. It's violated by our universe's history. Some physicists argue that the asymmetry isn't in the laws, it's in the boundary conditions. The universe has a past boundary, the Big Bang, with extremely low entropy. It has no future boundary, or at least none we can identify with low entropy. That asymmetry in the boundary conditions is what breaks the time reversal symmetry of the equations and gives time its direction. Remove that asymmetry and the picture changes entirely. Consider a hypothetical universe that started in a high-entropy state and was contracting toward a low-entropy future. In that universe, time's arrow would point in the opposite direction. Entropy would decrease toward the future as that universe defined it. In such a universe, white holes would be the natural objects, and black holes would be the pathological ones. White holes would form spontaneously from collapsing material. Black holes would require an extraordinary decrease in entropy just to come into existence. Every argument we currently make against white holes would apply, in that mirror universe, against black holes. The physics would be identical, only the history would differ. That realization is worth sitting with. The reason white holes don't exist isn't that physics prohibits them. It isn't that the equations reject them. It isn't that they violate some fundamental conservation law baked into the fabric of reality. It's that our universe happened to begin in a very particular low-entropy state, and that initial condition set the direction of time's arrow, and that arrow points relentlessly toward greater disorder, and black holes are downstream of that arrow while white holes are upstream of it. In a universe that started differently, we might be asking why black holes seem so implausible. This puts white holes in a strange category. They aren't like perpetual motion machines, ruled out by a law that applies everywhere and always. They're ruled out by context, by history, by the specific, contingent fact that our universe began in an improbably ordered state roughly 14 billion years ago and has been expanding and disordering ever since. Change the starting conditions, and the whole ledger flips. White holes aren't impossible because the laws of physics forbid them. They're absent because the universe started in exactly the kind of low-entropy state that makes black holes natural, and white holes a violation of everything we observe, which is a deeply different kind of impossibility. You cannot enter a white hole, but imagine, as a thought experiment, that you were somehow already inside one, present in that expanding interior, with the past singularity behind you and the horizon ahead. You didn't fall in. You couldn't have. Nothing can cross a white hole's boundary from the outside. So if you're inside, you were there from the origin. You emerged from the singularity itself, and now you find yourself in a region of space-time that behaves unlike anything in ordinary experience. The first thing to understand is the direction of time in here. The singularity is behind you. Not behind you in space, but behind you in time. It lies in your past, the way the Big Bang lies in the past of everything in our universe. You cannot return to it. There's no path that leads back. Every trajectory available to you points outward, toward the horizon, toward eventual escape. Think about what that means. Inside a black hole, the singularity lies in your future. Every path leads toward it. You can't avoid it. Inside a white hole, the geometry is reversed. The singularity is where you came from. The horizon is where you're going. You're not falling in. You're being carried out. This isn't a choice. It's geometry. Space-time inside a white hole is structured so that all future pointing paths lead toward the horizon. You can accelerate. You can fire a rocket in any direction. You can try to hold still. None of it matters. The interior is expanding, and you expand with it. Space-time itself is stretching outward from the origin point. Everything inside the white hole is moving away from everything else, not because of any force pushing things apart, but because the geometry of the interior is diverging. It resembles an anisotropic expanding universe, a small cosmos, a region of space-time born from a past singularity and flying apart in all directions. Now consider what you would actually experience near the beginning. Near the past singularity, space-time curvature would be extreme, unimaginably extreme. If quantum gravity prevents a true singularity, if the Planck scale bounce that loop quantum gravity predicts is real, then the curvature near the origin reaches some maximum finite value around 10 to the power of 93 grams per cubic centimeter. That's Planck density. At those conditions, neither general relativity nor quantum field theory gives reliable predictions. The two best theories in physics both break down. We simply don't have the tools to describe what spacetime looks like that close to the bounce. It's not that the physics is complicated. It's that the physics we know stops working entirely. Moving away from the origin, conditions become less extreme. The curvature drops. The tidal forces weaken. Tidal forces, remember, are what stretch and compress objects in curved spacetime. Near a singularity, the difference in gravitational pull between one side of your body and the other would be enormous, incomprehensibly enormous, enough to pull atoms apart, enough to pull the concept of an atom apart. But as the interior expands, as you move further from the origin in time, those forces diminish. Space becomes less curved, the geometry relaxes, the mathematics transitions from something barely describable to something approaching the familiar. There's something worth pausing on here. The interior of a white hole at late times starts to resemble ordinary spacetime. The curvature decreases toward the horizon. By the time you're approaching the boundary between the interior and the exterior, conditions might be close to flat. Flat spacetime is what we live in, roughly speaking, far from any massive object. Flat spacetime is calm. It's quiet. The horizon of a white hole, approached from the inside, wouldn't necessarily feel catastrophic. It's a boundary, not a wall. It's a one-way surface you cross, not with violence but with inevitability. And then you cross it. The horizon is ahead of you in time. You reach it not because you aimed for it, but because space-time gave you no other option. Crossing a white hole's horizon from the inside is the permitted direction. It's the only direction the geometry allows. You emerge. What you emerge into depends entirely on the nature of the white hole. If it's a stellar remnant, a black hole that has completed its quantum transition, you emerge into the universe outside it, into ordinary spacetime, potentially surrounded by whatever matter was orbiting the original black hole, whatever radiation was emitted during the transition. If the white hole interior is something larger, if it's the interior of the universe itself, as some cosmological models suggest, then the horizon is the boundary of everything, and crossing it means entering something we have no framework to describe. The sense of inevitability inside a white hole is total. Inside a black hole, an infalling observer might struggle, might try to reverse course, fire engines, send signals outward. None of it works. The singularity is in the future, and physics is ruthless about futures. The same ruthlessness applies inside a white hole, but in the other direction. The exit is in your future. The singularity is in your past. No engine, no signal, no decision changes that. You are being carried outward by the structure of space-time, the way an object inside a black hole is carried inward. Not pushed, not pulled, simply moved, because that's the direction time flows in this region of the universe, and time, in general relativity, is not negotiable. Most of physics is about choosing. You choose a path. You apply a force. You steer. Inside a white hole, that framework collapses. The direction is built into the geometry at a level deeper than force or choice. The past singularity already happened. The horizon is already in your future. The expansion is already underway. You're not a traveler navigating a landscape. You're a particle in a river that only flows one way. Inside a white hole, there is no choice, no decision, no possibility of turning back. The geometry of space-time carries everything outward toward the only exit, and you would emerge into whatever universe waits on the other side of that horizon. After everything, The mathematics, the thermodynamics, the instability arguments, the quantum gravity proposals, the cosmological implications, the honest answer to the question of whether white holes exist is that we don't know. That's not a comfortable place to end up. We've covered elegant mathematics, extraordinary geometry, and some of the most ambitious theoretical work in modern physics. And the conclusion is, we're not sure. No confirmed detections, no unambiguous observational evidence, no physical formation mechanism that classical general relativity can endorse. The thermodynamic walls are real. The instability arguments from the 1970s were serious, and they haven't been overturned. Eardley showed in 1974 that even tiny perturbations collapse a white hole before it can do anything. Zeldovich and colleagues showed that quantum corrections at the horizon diverge in ways that destroy the structure from within. These aren't minor technical objections. They're fundamental problems, and they explain why white holes spent decades filed under mathematical curiosities rather than physical candidates. Yet most observers overlook this. The theoretical situation has changed. It hasn't resolved, but it has shifted in a way that serious physicists take seriously. Loop quantum gravity predicts that black holes don't evaporate into nothing. They transition. The singularity at the core gets replaced by a quantum bounce, and the collapsing interior becomes an expanding one. That expanding interior is, by definition, a white hole interior. The black hole's event horizon becomes a white hole's horizon. The object doesn't disappear. It transforms. This isn't a fringe idea. It's a direct prediction of a well-developed theoretical framework, and it comes with a resolution to the information paradox that is cleaner than almost any competing proposal. The information that fell in doesn't vanish, it emerges. Quantum mechanics survives intact. Think about what that means for the scope of the question. We're not just asking whether white holes are real. We're asking whether quantum gravity is real in a particular form, whether singularities are physically avoided or physically realized, whether information is preserved or destroyed at the fundamental level. White holes sit at the intersection of three of the deepest unresolved problems in physics: quantum gravity, the black hole information paradox, and the origin of the universe. The stakes are not academic. The disagreement among physicists reflects this. Some researchers regard white holes as permanently ruled out. The arrow of time, the second law, the instabilities, they add up to an object that the universe simply doesn't realize, regardless of what the equations permit. The equations also permit many things that don't exist. Others, including Carlo Rovelli and collaborators working within loop quantum gravity, regard white holes not just as possible, but as inevitable. Every black hole that forms will eventually become one. The only question is when. For a stellar mass black hole, the transition timescale from the outside is staggering, potentially vastly exceeding our universe's present age. But smaller, primordial black holes formed in the early universe might be reaching that transition right now. That possibility is genuinely testable. Not by pointing a telescope at a single object and watching it turn into a white hole, but by looking for the statistical signature of these transitions across the sky. A black to white hole transition would release energy rapidly, potentially as a burst of high-energy radiation visible across cosmological distances. Fast radio bursts, gamma-ray bursts, brief energetic transients with no obvious source. These are candidates. The signal would be distinctive if we knew exactly what to look for, which requires a more complete theory than we currently have. But the search is not hopeless. It's constrained by our incomplete knowledge of quantum gravity, not by an absence of instruments. The cosmic microwave background offers another angle. If the Big Bang was itself a white hole event, a bounce from a previous collapsing phase, then the earliest observable light in the universe might carry imprints of that pre-bounce geometry. Anomalies in the CMB's polarization or temperature spectrum at specific scales could, in principle, carry signatures of a phase that preceded our observable universe. Cosmologists are looking. They haven't found anything definitive yet. But the instruments keep improving. The Simons Observatory, CMB-S4, future space-based detectors, these will probe the CMB at precision levels that previous generations couldn't reach. The next generation of gravitational wave observatories will also push further. LISA, the space-based interferometer planned for the 2030s, will detect mergers and events at mass scales and distances that current detectors can't reach. If white hole transitions produce gravitational wave signatures, and some models predict they should, LISA might be sensitive enough to catch them. We don't know. The theoretical predictions aren't firm enough yet to say exactly what the waveform would look like, but the window isn't closed. What we're left with is a genuine scientific frontier, not pseudoscience, not speculation for its own sake, but a real open question at the edge of what our best theories can currently answer. The resolution will require a better theory of quantum gravity than we have. It will require knowing what actually happens at Planck scale densities, whether singularities form or whether quantum effects prevent them. It will require understanding the information paradox at a level we haven't reached. These are hard problems. Decades of work by some of the most capable physicists alive haven't closed them. That's not a failure. That's what a real frontier looks like. What we can say is that the universe is under no obligation to make things easy for us, and white holes, whether they turn out to be real or remain permanently theoretical, have already forced us to think more carefully about time, information, entropy, and the origin of everything than almost any other object in physics. The history of physics is full of objects that existed in equations for decades before anyone managed to detect them. Paul Dirac wrote down the mathematics of antimatter in 1928. No one had seen it. The positron was detected 4 years later. Einstein's general relativity predicted gravitational waves in 1916. We detected them in 2015. The Higgs boson was predicted in 1964. It took nearly 50 years and the largest machine ever built to confirm it. The equations were right. The universe had been doing these things all along. We just hadn't looked carefully enough yet. White holes sit in exactly that position right now. The mathematics is valid. The equations produce them naturally, without any special assumptions, without forcing anything unusual into the theory. When you write down the Schwarzschild solution and extend it completely, white holes appear the same way antimatter appeared in Dirac's algebra, not as a guess, not as a hope, but as an unavoidable consequence of the math. And the history of physics says that when something appears that way, you should take it seriously. Think about what it would mean if they're real. Every black hole that has ever formed, every stellar collapse, every neutron-star merger, every supermassive object anchoring a galaxy at its center is slowly transitioning. The timescales are almost incomprehensible. A stellar mass black hole might take longer than the current age of the universe to complete its transition. Longer than that. The universe is about 13.8 billion years old. Some of these timescales dwarf that by factors we don't have names for. But time doesn't stop. The universe doesn't run out of it. And according to loop quantum gravity, the transition happens. Every one of them eventually becomes a white hole. Every one of them eventually begins to release what it took in. That means the universe isn't destroying information, it's holding it. For unimaginable stretches of time, locked inside geometries that nothing outside can penetrate, everything that ever fell into every black hole is preserved, not lost, archived. And at some point, on timescales that make stellar evolution look instantaneous, it comes back out. The universe is not the information-destroying machine that Hawking's original calculation suggested. It's something stranger, and in a way more careful than that. We live on a planet with a diameter of about 8,000 miles. Our sun, which dwarfs us entirely, is one of roughly 200 billion stars in the Milky Way. The Milky Way is one of at least 2 trillion galaxies in the observable universe. From that position, that almost absurdly small vantage point, Human beings sat down with mathematics and derived that there might exist an object that operates as the exact inverse of a black hole, that carries within it a past singularity rather than a future one, that cannot be entered from outside, that resolves a paradox sitting at the intersection of the two greatest theories in modern physics. We derived that this object's interior geometry is mathematically identical to an expanding universe emerging from an initial singularity. And then we looked at the universe around us, expanding outward from a past singularity, impossible to run backward, carrying everything that has ever existed away from an origin point, and recognized the geometry. That recognition is not a minor thing. It's the kind of moment physics produces occasionally, where two descriptions that seem completely unrelated turn out to be the same description, where the object you're trying to understand and the place you're standing turn out to share the same mathematics. It doesn't prove anything. The Big Bang might not be a white hole. Our universe might not be the interior of one, but the resemblance is precise enough that serious physicists have spent serious careers examining it. That alone says something. Black holes are real. We have images of them. We have heard them merge as gravitational waves passing through our detectors. They compress matter to densities our instruments cannot probe, and our theories cannot fully describe. And embedded in the same equations that produce black holes, inseparable from the same solution, is their mirror. Same mass, same geometry, everything reversed, one that only absorbs, one that only emits. The universe's equations generated both. We may already be inside one, expanding outward from a past singularity, carried by the geometry of space-time toward whatever lies beyond the horizon, which is, by any reasonable definition, exactly what the universe looks like from where we're standing.